Alright, so it's being streamed, meaning it's getting recorded now. So that's all good. Alright. So what we'll do today is to start with upper bound. It's a concept that we talked about last time, but it was about a week ago, and so it's probably a good idea to restart with that. I think Wednesday is also a holiday. Let me double check on that. May not be Wednesday. Let me double check. It's the 11th, so I think that would put it on Thursday. So Thursday is Veterans Day. Let me double check. Yeah, so Thursday is Veterans Day, so it does not impact this class at all. Yeah, that only affects 310. That is correct. All right. We got about 2 more minutes before the class starts. So if anyone has wants to go over the exam, I suppose we can do that. But the exam is really not that much different compared to the practice exam. So, I mean, I don't really feel particularly necessary to talk about it, but if anyone wants to talk about it, we can do that. Besides, I'll be using, sample questions that are very unlikely to be the ones that you have. So, not sure how helpful that's going to be. All right. Still got 1 minute and 30 seconds to go. Alright, so I suppose I can talk a little bit about what goes after the big O notation. It kind of depends on how much time we have left. I wouldn't mind a few. Alright. A few of what? The exam questions? Okay, we can talk a little bit about that. Let me dig up the questions first. Alright, so I'm right there already, so that's good. X2. Alright, so this should help. There we go. Alright, so we are starting now. Since someone mentioned to go through a few of the questions, we'll go ahead and go through maybe 1 or 2 of each category instead of every single one. So question 1 is a fairly typical question that was asked in the practice exam too. There's a little bit of difference in terms of the description of how people should answer the question. So I'm gonna read through the entire thing from the beginning. Relation R is this particular set. It is defined over X, which only has 0, 1, and 2 as its elements. Describe relation R in the following terms. True or false, do not leave it blank. If it is false, point out why it is false using a specific example that makes the applicable quantified criterion statement false. Whew, okay, so this is a phrase to refer to the for all thing, that I use to describe each property of a relation. So you kind of have to go back to the definition. This is my way of saying, okay, you need to go back to the definition. And I even illustrate with an example, which is if a property, let's call it UUP, which stands for utterly useless property, is true if and only if, and I instead of using the for all symbol, because it's a little bit hard to use the for all symbol in HTML. I did not create these questions, or they are not generated in Markdown, which would have been a lot easier. I was using HTML, and that's a little bit harder, but it still carries the same meaning. So right here we have for all EF in X, ERF, and FRE. Now there's no such property that we have talked about, and that's why this is an invented, utterly useless property, because it is not something that we have actually talked about. So if this is actually a property, and you find that when E equal to 6 and F equal to 7, only 6, 7 is in R, but 7 and 6, 7, 6 is not in R, then your answer should state when E equals to 6, F equal to 7, ERF and FRE is false because 7R6 is false. Okay, there's no such tuple in R in that case. So that is the kind of explanation that I would be expecting in this test. Okay, because each question states what I'm expecting in the answer. An answer of false to a property that does not connect with the corresponding quantified statement will not receive full points. And that's all I said. It's not going to be receiving full points, which can start with a 0. So it can be 0, can be 1, can be 2, can be 3. It's just not going to be 4 out of 4. All right. So when they do satisfy, we just say yes. So when they do satisfy, you just have to say true. Because it's the lack of evidence that it does not meet all the requirements. And all the properties that we have looked into, reflexive, symmetric, anti-symmetric, transitive, and comparable, they are all defined using the universally quantified statement, which means finding one counterexample is all you need to say that it is not true. But if you cannot find a counterexample, then it is by default true. Okay, so Jonathan W. In the previous class, before the exam, made a very good point. Okay, the lack of contradictory evidence means it is by default true, and that's why the MT relation itself actually meet quite a few of these requirements. It is symmetric, it is anti-symmetric, it is transitive, it is just not reflexive, and it is also not comparable. But it does meet the middle three of the properties. All right, you can copy and paste from the module linked from Canvas. So that means you can just copy and paste my equations, slap it into here, and say in this case when E equals to this, F equals to this, and then G equals to this, the quantified statement itself is going to be false. And since I can find one contradiction, that property is false. All right, so let's go ahead and work with this one first. Okay, and we're gonna, let me see, where's my Joplin? Joplin, where are you? Oh, right there. All right, so here's the Joplin screen, and I will copy and paste the set into Joplin. So copy, and this is let's see, this is exam 2. Okay, exam 2 review. I'll just say exam 2, and then the relation is this one, and we want to find out of the properties that we have talked about, which one is true, which one is false, and if it is false, why it is false, and how we want to format the answer. All right, so copy this whole bunch, paste it into here. Let me see how it's going to be pasted. Doesn't quite work, right? That's okay. We'll just put an asterisk here. Asterisk, asterisk. All right. There we go. Oh, okay. There we go. All right. So the first one we're going to look into is reflexive. So now you're going to have to quote the reflexive definition, or at least if you find that this is not reflexive, you have to tell me what is the condition that is false when what is E and what is G. Okay, so you can kind of take a shortcut, but it is still necessary to refer back to the definition. So if your explanation does not refer back to the quantified definition of the property, then you're not going to get your full points. All right, so to restate, okay, since I have all the time in the world, I'm going to restate, but you can copy and paste from the notes directly. It's just like that. So the reflexive is basically saying for all EF in X, oops, in is like that, X, okay, I'm putting in a, then we want the following condition to be true. Oh, actually, it's just E. We don't even need an F in this case. So that makes the counterexample very easy to explain, because you just have to say, hey, when E equal to this, ERE is missing, okay, or EE as a two tuple is missing, and therefore it is not reflexive. So but I'm gonna finish this first, okay. So EE has to be in R in order to be reflexive. So we'll also state a little bit more clearly: reflexive if and only if the following is true. Alright, so given this is the definition, and you can look up the definition in the notes, okay, and copy and paste it. So in this case, we are going to ask, okay, can we find 0, 0? Because 0 is in X, so we want 0, 0 to be in R. Oh, we are missing the curly braces, because curly braces are absorbed in LaTeX because it has special meanings. Okay, there we go. So 0, 0 is fine, not a problem. 1, 1 is missing. Okay, so now we just say, when E equals to 1, 1, 1 is not in R, and therefore not reflexive. Oops. There we go. No, you do not have to define reflexive, but you do have to mention what is false. That is making it not reflexive. In other words, 1, 1 is not in R when it is required, because this is the whole point of whether a relation is reflexive or not. So you still have to relate back to here. There we go. I made mention of the quantifiers, but in a very sparse language. For example, instead of writing the for all part, I'd say this is not true, because when E equals X, F equals Y. Yeah, that would be fine. Yes. All right. Yeah, that would be fine, because it's still referring to the statement that is quantified. You don't have to include the universal quantifier, but you do have to refer to the statement, which is the essence of, okay, what makes this relation reflexive? So there we go. Okay. All right. All right, so let's look at symmetric. So I'm just going to do this one more time, just so that, you guys know what is symmetric. So symmetric if and only if. So in this case, we do need two variables. So we say for all EF in R, and this time the statement that is being quantified is going to be EF if and only if. Okay, so at this time I'm going to use the double-sided arrow, which is left, right arrow, FE. And I'm forgetting a comma in the other one. There we go. All right. So if you remember to look up the notes, you will see that this is the actual definition of whether a relation is symmetric or not. So in this case, we're going to say, okay, well, let's find out all the different ways to assign values into E and F. They can be the same. Okay. So when E and F are both zeros, we are fine, because 0, 0 is in it, not a problem. What if E is 0 and F is 1? 0, 1 is in here, but 1, 0 is not. Okay, I'm done. Okay, because if you want to use counter example, all you need is just one single counter example, and that's all you need. So you can now say, E equals to 0, F equals to 1, and in this case, E comma F is indeed in R, but FE is not in R. Okay, I'm gonna have to break it up. I'm just trying to think of how I'm gonna write this. Oh, I know how to do it. Okay, so I'm gonna use a simplified format here. So we will say ERF is true. FRE is false. So that makes ERF if and only if FRE is false. There we go. So that's one way to put it. Does everybody understand this part here, other than the typo that I'm putting here? Any questions about this particular explanation? So if you don't mention the definition of symmetric, then you will have to tell me that somehow you have to include the if and only if. Because the whole idea of why R in this case is not symmetric is because 0, 1 is here, but 1, 0 is not in here, but it ties into the if and only if of the original definition. So the if and only if has to be part of the explanation. Is that okay? Does everybody understand the requirement here? Maybe. Okay, cool. Alright, so what about anti-symmetric? So in the case of anti-symmetric, I'm going to define it one more time here. So anti-symmetric if and only if we only need two variables also. So we say for all EF in R, and then what is required in this case is a little bit more complicated than the previous two properties, because in this case we say EFR and FRE has to imply E and F are the same. So that is the definition. Yes, I know in my notes I say EF as a 2 tuple in R and FE as a 2 tuple in R, but that's just a different notation of whether a particular value relates to another value or not. So in this case, let's check out whether this requirement is holding true. So when E and F are both zeros, we don't have a problem, because even though ERF and FRE are both true, both of these are true, and therefore the conjunction is true, but the equality is true as well, so we don't have a problem. When E is 0, F is 1, we don't have a problem either, because we only have one of them, which means the conjunction is going to be false. When the conjunction is false, which is the left-hand side of the implication is false, the implication is going to be true. Not a problem. Same goes when E equals to 1, F equals to 2, not a problem. When E equals to 2, F equals to 0, not a problem. When they're both 2's, not a problem either. So I don't see a problem. So I'm just going to say it is true. Okay, so in this case, we will say not symmetric. So in this case, it is anti-symmetric. So we'll say it is anti-symmetric. And then for transitive, you need 3 variables. So that means, okay, so the definition of transitive is for all EFG, and I'm going to put an $and $sign here first, in R, and this time we have an implication, and we also have a conjunction on the left hand side. So we have ERF and FRG, and that has to imply ERG. There we go. So let me scroll down. And why? Oh, okay, the extra space is killing it. There we go. So let me double check, make sure this is correct. Yep, it is correct. All right. So let's check this one out. Okay, is this relation transitive? So we'll kind of quickly glance through this, and let's see. 1, 2, 2, 0. All right. So I know it is not transitive because when E is 1, F is 2, and then G is 0, then 1, 0 is not there. So that's why it is false in that case. So the answer to this question is when E equals to, what was it again? 1. Okay, 1, 2, 0. Okay, there we go. When E equals to 1, F equals to 2, G equals to 0, we will have E, RF, and FRG is true, but okay, I'm just gonna use the same format here. ERG is false. So this means so we want to basically quote the entire expression that is quantified. So we're going to quote this entire thing. So just a copy and paste in this case. This whole thing is false. And then the conclusion is it is not transitive. There we go. So do we have any questions about the answer to the property transitive, why it is not transitive, and also how it is explained in this case? No questions? So once again, the answer has to tie into the expression that is quantified. We have to basically show the expression that is supposed to be universally quantified. We can find one instance. Okay, we can bind values into E, F, and G in this case. Find one single instance where that particular expression is false. All right, so we're moving on to the last one. I mean, if you guys have any questions, put it into the text channel. So we have comparable in this case. Comparable is actually easy. It's almost like the utterly useless property, the UUP, except instead of an and, this time we have an or. So we say comparable if and only if the following. So we have for all E, F in R, and the actual expression that needs to be true, regardless of how we bind values into E and F, is going to be E, R, F, or F, R, E. So that is the definition of comparable. So in this case, we can probably very easily find out that it is not comparable. And I already said that you cannot use because it is not reflexive, therefore it is not comparable, but you can use the same example. Okay, so for the same reason that we can state here that it is not reflexive, we can use the same example. The lack of 1, 1 is why we can say it is not comparable. So we can basically just use the same value, but this time you have to bind the value of 1 into both E and F. So now we can say when E equals 1, F equals 1, then E, R, F. Oops, let me use the equation dollar signs, and then I was trying to use the cursor key, but I hit the page up page now instead. So E, R, F, or F, R, E is false. There we go. And as a result, it is not comparable. There we go. All right. So do we have any questions about this one? About how I answered the first question. All right. Very good. Yeah, it is kind of, it's not just kind of like the practice exam in terms of what I'm really asking is identical to the practice exam, except in this case, I was a little bit more explicit about how I want the answer to look like. So that's kind of the only difference between the practice exam and the actual exam in this case. Oh, okay, we can hit one of those, sure. So the next one is one of those. So we'll answer question number 2. And before we do that, let me put a header here and say this is for question number 1. So pound Q1. Not that it is going to be useful to you to know that this is question number 1, because it is not going to be your question number 1. It's very, very unlikely to be your actual question number 1. But it's nice to have a header to kind of remind us, okay, what is this stuff here? So, okay, let's deal with question number 2. All right, so question number 2 is, X is pretty much all, 0, 1, 2, for all the questions. So this part is pretty standard. But this time we want it to be partially ordered, is not comparable, and it is also not symmetric. All right, so I'm just going to copy the part that is essential, and then we'll try to figure out something on the other side. And I would try to explain to you how to make up for something like that. When I try to answer these questions, the thinking process in my head is really just, it's not exactly in individual steps. It's not like I'm following an algorithm, a specific logic to do it. It's kind of like the brain just kind of fires off in many different directions at the same time, and then it just kind of comes back and say, okay, this might work, and then I just have to verify that it does work or not. So I'm not really sure how I can explain these in a way where you can say, yeah, I can see how to do this now, but I'll try my best. All right. Yeah, exactly. Jonathan is correct. It really has something to do with personality types. If you guys have taken the test, the MBTI, the Myers-Briggs type indicator, this part kind of falls into the N category. The second letter is either S, sensing, or N, which is intuitive. It's the N that makes, especially NE, extroverted intuition, that that spells out that a person can explore, many different possibilities and in different directions at the same time. Subconsciously, this is not something that I will say, okay, here's an algorithm, okay, for each blah blah blah, if blah blah blah, and then blah blah blah. Nope, it's just psh, it kind of works by itself, subconsciously. All right, so let me see if I can systematically explain how this is going to work. All right, so we want it to be partially ordered. So the first thing you need to do, this part is easy, okay? Because you just have to look at what is partially ordered. So we know partially ordered needs to be reflexive. We know partially ordered has to be anti-symmetric. And we also know partially ordered has to be, what was the next one? Transitive. Right, there we go, transitive. There we go. All right, so now you look at these 3, okay, and you ask, how am I going to make this happen? Well, being reflexive means you have to have 0, 0, 1, 1, 2, 2. Okay, so those are required, just because of being reflexive. So you have 0, 0, 1, 1, and 2, 2. There we go. All right, so now the question is, what else do we need? Well, the first thing is, what is it missing right now? You go like, is it anti-symmetric at this point? Yes, it is actually anti-symmetric at this point. And then you ask one more thing, is it transitive right now? The answer is yes, it is also transitive. So we are done. So I just got lucky, okay? So is that okay? Does everybody understand, how I got to this solution? The actual sequence of reasoning in this case, but I got lucky because this one is just like, oh, so that means just the minimum set, okay, the minimum relation just to be reflexive automatically makes it meet the other two requirements, and so it's pretty easy. All right. Yeah, it is my cat. Every villain needs a cat, or two in this case. That reminds me of Austin Powers, the villain in Austin Powers. He has a bald cat. My cats are not bald. Oh, it's definitely symmetric, but it's not needed, so it's okay. Whether it is symmetric or not is not is not important. All right. All right. Since this is the kind of question that people might have more problem with, let's pick another one and see if this one is a little bit more challenging. Question number 4. It requires not symmetric. Nope. Nope. No. 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 Nope. Partially ordered says it needs a relation to be reflexive, anti-symmetric, and transitive. Those are the 3 requirements for a relation to be partially ordered. So
But I
not
thought requirement, sorry, Professor, I thought the requirements say is partially ordered, not comparable, and not symmetric for R.
mm, well, let's check, right? I mean, if I actually typed that in my notes and I was wrong, I would apologize.
No, Professor, is not from your note. It's
Oh,
from the question number 2. It say R is
oh, okay. So I
not
missed
symmetric.
part of the question. Oh, you're right. Okay, cannot be anti-symmetric. Thank you. Okay, so on is correct. I would have gotten a B because I just missed something. I did not. Okay, not comparable, we are good, right? But I forgot about not symmetric, which is a requirement. Thank you, thank you, thank you for reminding me of my own question. I missed one part of my own question. So yes, I would at the best be a B student in my own class. I don't know what else to say, but in this case, we also have to remember to add not symmetric. Yes, you can probably hear my cats fighting in the background. Yeah, one is hissing at the other one. It's okay. They're not gonna kill each other. Not yet. Alrighty. Let's find. Okay, so we just want it to be not symmetric. So that means we just have to add something, where like that, right? So let's double check. Is it still reflexive? Yes, it is still reflexive. Is it anti-symmetric? Yes, it is still anti-symmetric because until we have 1, 0 in it, there's no way for this to be not anti-symmetric. Is it transitive? Yes, it is transitive. Is it not symmetric? It is now not symmetric. Okay, so hold on 1 second. Let me settle the dispute first. All right, sorry about that. It's not done yet, but I opened the screen room door, so if one needs to escape into the screen room, they can, he Well, he can do it. Both are he's. They're brothers. Yep, they are actually related. All right. Yep, they're still fighting. They're just batting at each other. One is running. So, okay. All right. So back to this one. Yes. So Oren is correct. Oren is being very being very careful. Okay. So that's good. Thank you. No, I did not just randomly try something. I know in order for something to be not symmetric, because of how symmetry is defined, okay, because this is how we define symmetry. So that means in order for something to be not symmetric, we will need one side to be true but the other side to be false, right? So we just have to pick something where one side is true but the other one is not false, and I just so happen to choose E being 0 and F being 1, and that's about it. But it all depends on the definition of if and only if, and that is the key to understand how to just add one element in order for it not to be symmetric. Oh yeah, I mean you can. Oh here, okay. Here's another. Here's a variant of the question that I asked. Okay, so I can even ask you a question of what is the largest R you can get before it becomes and still meet all of these requirements. Okay, because I just gave you the minimum relation where it meets all the requirements. So now you can say, oh, I can add 0, 2 into it, and there's no problem in this, right? So I can add 1, 2 in it, not a problem. And I can add, let's see, if we have to make sure it's not comparable, so we have to be kind of careful with this one. Now I think we have a problem already. 0, 1, 1, 1, 1, 0, 1, 2, and then 2 relates to both. So now we have a problem. Okay, let me just kind of stop right here and explain what the problem is. The problem is it is now comparable. It is now comparable because 0 relates to itself, relates to 1, also relates to 2, 1 relates to 1, relates to 0, also relates to 2, 2 relates to 2, 2 relates to 0, 2 relates to 1. So it is now comparable, but we don't want it to be comparable. So that means we have one too many elements. We just cannot have this one here to make it comparable. So I think this is the largest set you can have to meet all the requirements. Yep, there we go. Yep, well, in this case, it would seem to me, I mean, this is not a formal proof by any means, but it would seem to me that if we add anything else, we would have a problem because it basically not meet all of these requirements anymore. Reflexive is never really a problem, but if we are not careful, we can add one more thing and make it not anti-symmetric anymore. We can potentially add one more thing here and make it not transitive anymore, and the symmetry is that's not the difficult one because it's very easy to break symmetry. It's just hard to fix it. But the problem is comparable. If we want it to be okay, that's my bad because we want to say not comparable, not symmetric. So not comparable is going to be the problem because if we add one more thing in here, it will either break anti-symmetry or it will break not comparable. So one of these two requirements will not be met anymore if we just add one more element to it. I mean, you can think about it too. I mean, you can think about, okay, what possibly can we add at this point, right? We can add 1, 0. If I add 1, 0, it's not going to be anti-symmetric anymore. We can add 1, 2. So if I add 1, 2, it's not going to be not comparable anymore because it will be comparable at that point. So that's not going to work. If we add 2, 1, same thing. Okay, if we add 2, 1, it is also going to be comparable. It will break this particular rule of not comparable. And that's about it. I mean, those are all the elements I can add to the set at this point. Is that making any sense? Oh, I forgot about 2, 0. If I add 2, 0, same thing. It is not going to be anti-symmetric anymore. So exhaustively, I can show you that, for this specific case, okay, when x equals to 0, 1, and 2, this is the largest set that can still meet all of these requirements. If I add one more thing, okay, it's going to break at least one of these requirements. All right. So any questions? All right. So we're going to go to the next example. We'll try, let's see, question number 4. Okay, so question number 4 has the following requirements: is not reflexive, is not anti-symmetric, is transitive, is not comparable, and is symmetric. That sounds like fun. So we'll tackle this one. Okay. All right. All right, so not reflexive is pretty easy. We just have to make sure that one of the 3, 0, 0, 1, 1, 2, 2, one of the 3 is missing, and that's all we need. So that is, I'm not too concerned about that. Not anti-symmetric means, we're gonna have 0, 1, 1, 0 in it. That will make it not anti-symmetric. We want it to be transitive. We want it to be not comparable, and we also want it to be symmetric. Okay, so I'm just gonna do one thing here. Okay, so I'm gonna break satisfy one of the requirements one at a time, and then I'll see what else I need to do. So just by introducing these two, it will be not anti-symmetric at this point. It is not transitive, so in order to make it transitive at this point, I will need 1, 1 and 0, 0. Does everybody understand why 1, 1, 0, 0 are needed? Once we have 0, 1 and 1, 0, why 1, 1, 0, 0 are needed in order to be transitive? Okay, excellent. All right, so now we have met not being reflexive, not being anti-symmetric. It is transitive. It is not comparable at this point, and it is also symmetric. I think I got my answer. So, any questions about how I got to the answer? You kind of have to put things in it first, okay? And to say, okay, if I want it to be not anti-symmetric, what do I need? Well, you cannot have an empty relation, because an empty relation is by default anti-symmetric, because you cannot find a counter example to make it not anti-symmetric. So I need to create a case to specifically make the condition false. Okay, the universally quantified expression, I need to make it false. So these two elements here is put in here just to say, okay, now it is not anti-symmetric. Then I look at the other requirements and go like, okay, what else do I need to do in order to meet the other requirements? So I need it to be transitive. So in order to be transitive, if E is 0, F is 1, and G is 0, I need 0, 0 to be here. On the other hand, if I say E equals to 1, F equals to 0, and then G equals to 1 again, I need 1, 1 to be here. So I need 1, 1, 0, 0 in order to be transitive, at the same time not anti-symmetric. Not comparable is pretty easy, because 2, 2 is missing, right? If I don't have 2, 2, if I don't have 1, 2, if I don't have 0, 2, it is definitely not comparable. If 2 is not mentioned at all in R, then it's not going to be comparable. So I just need to make sure it is also symmetric at this point. It is symmetric. 0, 1, 1, 0, they're mirrors of each other. 1, 1 is mirror of itself, and then 0, 0 is mirror of itself. So it is definitely symmetric at this point. So that's how I would answer question number 3. All right, so I'm going to move on to a different type of question, which is one of the proof, thing. So I'm going to use this one, question number 7. We have psi being this thing. All right. So these are basically just your Boolean algebra kind of question, and this one is question number 7. All right, so question number 7, and with these, I am going to use. I'm just going to put spaces over here, so it is. It's just not going to do any formatting. There we go. So now we first try to get rid of the implication. That's usually how I get it done. Doesn't mean that you have to use the same sequence. Okay, so I'm gonna use the next line to say it equals to this. And the way I usually do it is I copy and paste first, and then I go back and change a few things, because this way, I don't have to worry about me introducing, and it's harder to introduce an error this way because it's copied and pasted. All the components are here already. So immediately I recognize I can do a simplification. So I'm gonna paste again, and the simplification says double negation can go away because it cancels out itself. All right. So from here, this negation here, that applies only to Q, and so we have a not Q on the outside, and then we have a conjunction, and then the other side of the conjunction is P plus R, and we probably need to distribute it at this point. Okay, so we'll go ahead and distribute that. So after the distribution, once again, you'll copy and paste first, and then we just replace the part where we are working on. Alright, so the part that we're working on is this part here. We're trying to use a distribution to take care of this part. So what we end up with is P not Q, or let's see, okay, not QR. So now that part goes away, and I don't need extra parentheses because of the priority of the operators. So now we got this, and then the plus R, we can remove the extra parentheses here because of the associative law. So without these things, we have a gigantic OR operation. So at this point, we can do distribution again. And in this particular distribution, we're just going to distribute everything. You can do it, you can do a FOIL first and then do the plus R, as the last thing to do. Or you can, kind of combine all three at the same time. So I'm going to do it in a more systematic way, which is FOIL first. So we'll do a FOIL with this one first. So the FOIL of that one. Okay, so that is unnecessary. So I was taking you guys through the park here because I can just do a distribution right here. So the distribution I'm doing here is going to be distributing the plus R into each one of these and then move the conjunction outside. So this will end up with not Q or R and P or R or R. There we go. There we go. Okay. Does everybody see how I just did distribution over here? Alright, cool. Alright, so this is CNF. It's not exactly optimized, but we can just kind of use one more step to make it look a little nicer. There we go. Because R or R is just R, so I just kind of simplify that out. Alright, so now it's time to deal with phi. But phi needs to be negated first, so we need to find out what is the negation of phi. Alright, so phi itself is right here. Okay, so we take a look at this. Alright, copy and paste. There we go. and then we put a negation on the outside right here. Alright, so the rest is about the same as what I just did. Okay, there are only so many tricks you can use, in this case. So the first thing I do is to get rid of the implication. So I turn the implication into a or, and then put an extra negation to the left hand side. And then what we do here looks like we can use De Morgan's law. So you can apply De Morgan's law from the outside in or the inside out. Okay, it's all up to you, because this negation here is actually applied to this or over here. But then we have these also negations applied to these disjunctions. So you can work from the inside out or from the outside in. I'm going to work from the inside out. Okay, so that means I'm going to take care of this negation and use De Morgan's law to distribute the negation to the disjunction, and the same thing over here. So I'm applying De Morgan's law twice, but on different sub-expressions in this particular step. So I take out this negation, put the negation on the inside, and then change the disjunction into conjunction. Same thing over here. Take out the overall disjunction negation, distribute the negation to each individual component, and then change the disjunction into a conjunction. I don't remember how I did in my exam. Can we see our exam again? Yes, I would even upload the correct answer to your exam. This part for questions, for the last 3 questions, I don't have the derivations. My automatic script does not generate, does not solve these things automatically. Actually, it can, I just haven't gotten that part written yet, because the way it works is it actually generates the CNF first, and then it works backward to give you what you see in the question. So actually it does have all the steps in between, but I don't have the script. The script doesn't have the code to save all the steps in between, so I don't have, it cannot quite do it yet. Okay, that's the bottom line. It cannot quite do it yet. I'm still teaching this class online next semester, so maybe I will have time to fix that at some point. There we go. Alright, so now we just have to apply the negation of the outside to the inside. So, so now we take out this negation and then change this conjunction, disjunction into conjunction, and then turn these two into negations. And the next step is the last one in this case, because now I can apply De Morgan's law to this part here, and it becomes a disjunction by itself. It becomes not P or not Q, and then the other one becomes not P or not Q, and then we can simplify. Okay, one more step. We can just go ahead and simplify this to take out all the double negation. Oh, okay, so we have the extra P here. Get rid of the double negation, get rid of the double negation, and there we have it. Forgot to add P. Did I? Oh, okay, I see. Okay, gotcha. Alright, so now we have one CNF from psi itself, and we have one CNF from the negation of phi. It's time to make what I call the super CNF. So psi and not phi is just going to be the concatenation of the respective CNFs. So we just copy and paste it. Now, obviously, I really don't know the answer to this particular question, so we're going to have to go through resolution, okay, until we either get to the contradiction, which is the 0, or until we say, okay, there are no new products that we can make out of resolution. So in this case, Q is the only one that can do any type of resolution because we don't have any negation of P, but we do have Q and the non-negative version of Q. So we'll go ahead and apply, resolution. So the first one is I prefer to do this kind of in a more systematic way. So I look at the first one and then look at it and say, can we resolve with the second one? No. Can we resolve with the third one? No. Can we resolve with the last one? Yes. Okay, so since we can resolve with the last one, we'll generate the last one, which is, let's see, the Q and the not Q kind of quote unquote annihilate each other, and P or R is left. So there we go. So this is the extra term as the result of the application of resolution. And if I want to be clear, I can indicate, how I got. Yeah, this part doesn't work very well. I think Joplin doesn't track the cursor very well when it is only spaces. So this not Q is being resolved with this Q over here. So what is left over would be the P or R being left over. So now we look at this and then we say, okay, so what else can we do for resolution? We have exhausted everything that we can resolve with the first term. So now we look at the second term, P or R, and there's nothing you can actually resolve with this one. We now look at the third one. The third one can resolve with the fourth one. In other words, I can kind of see that this is a dead end, but I still have to go through all the resolutions possible before I say, oh, at this point we are out. Okay, there's no way we can resolve any further. Alright, so I'm gonna have to position the caret until we get to this guy, and it's gonna resolve with this guy over here. And the result is just a single P as the result. So we take this entire thing, oops, oh, wrong key, and then paste it over here, adjust the spacing, like that, and we have one extra term of P over here as the result of this step of resolution. And at this point, this cannot resolve it with anything else. This one cannot resolve with anything else. This one cannot resolve with anything else. This one cannot resolve with anything else. So we are done. So now that we are done, we still have to write the conclusion, right? So we can say, since psi and not phi cannot resolve to false, phi is not a theorem. Now, technically speaking, you should say phi is not a theorem of psi, but if you just say phi is not a theorem, that's fine, not a problem. Alright, nope, we are not gonna take row today. So, for those people who show up just to make sure that they do not miss the row taking activity, I apologize. No, not really, but I'm gonna say it. Alright, so are we good here? I mean, does everybody understand how to answer the last three questions? They're basically the same kind of format, just gonna do this over and over again. Alright, cool. Exam 3 is not going to be cumulative, which is, I have to say, it's not good news. Okay, if the final exam is not cumulative, that means retroactive mastery of something that appeared in exam 1 and exam 2 is not going to help because it's going to be new material. So exam 3 is not going to be comprehensive, but it is intrinsically comprehensive in a way. So the concepts that we have learned up to this point, which has to do with the set notation, operations on set as a variable type, the meaning of implication, the meaning of all of the Boolean operators, all of that stuff is still essential to the final exam. So from that perspective, even though I won't be asking questions that are specifically just testing whether you understand what a union is, or what an intersection is, or what a in as an operator is, they are basically just used in the algorithm that will be in the final exam. So from that perspective, it may not be as it may not be actually a good thing that it is not comprehensive, because now people cannot go back and say, okay, now I have remastered all of these concepts. So for a comprehensive final exam, those people can say, yeah, I'm guaranteed to be able to get some points from those things that were in exam 1 or exam 2. It's all going to be new stuff in the final exam. All right, so I'm just looking at the time here. I think we're done with exam 2. Is that okay? I mean, does anyone want me to kind of go over anything else in exam 2? The resolution. Um, Well, that's pretty much it. Okay, you look for two disjunctions where one disjunction has the negation of a variable, the other one has the non-negated version of the variable, and then you join those two, as in concatenation, but you take out the variable where it is non-negated on one side, negated on one side and then non-negated on the other side. Whatever is left becomes the new expression. So that is my answer to the resolution part. Oh, okay. For the relation part, it doesn't have to be quite as explicit as what I put here, but it has to relate back to the definition. That's basically what I'm looking for. Is do you guys can you relate your answer back to the definitions in the quantified form? So that's basically what it is. Alright, so the next question is, let's just say that not phi includes the term Q or R. Alright, so if it includes the term Q or R, it's not going to help, because having the term Q or R is not going to help us with resolving to false. Because you can attach it right now. I mean, you can just say, okay, now this part, I'm going to put in square brackets, because it's not really a part of the original question. But if you have, Q or R in here, it's still not going to help, because all it can do in this case is to give you the single term R, because this term here can resolve with this term over here, giving you just R as a term. But because we don't have a term of not R anywhere, so we are still not, it's still going to be a dead end. So it's not going to help. Oh, okay. If you have not P, somewhere, if, we can, it can be resolved, because, this P is already singled out. So if we have not P, in the original, CNF, then we would be able to resolve it, in the next step. All right. Question 8 will resolve to false. All right. So I'm gonna let you guys do it, and then we can talk about it next on Wednesday. How about that? Because I think it's probably better for you guys to do it first, because just observing me doing it, is not the same as having you guys to kind of work on it too. All right, so I'm gonna, at least for now, conclude the discussion of exam 2, and then we are now getting back to the concept of an upper bound, and how how most people see the big O notation is not really quite how the big O notation is defined here. So we can see how big O is really giving you a set of functions, okay? Because f of n is actually a function of big O of g of n. And in order for f of n to be an element of big O of g of n, in other words, the way we define a big O notation is f of n divided by g of n, and you take the absolute value of that, and then we use lim sup. So lim sup is kind of just saying the minimum of all the maximums, and when we say the quote unquote the maximums, we are basically just saying, okay, let's find the maximum starting at different places of the sequence. That's all, how we got all the quote unquote maximums. So if you look at the minimum of all the maximums, and it turns out to be less than infinity, which means it is a particular concrete value. Okay, it can be 6, can be 16, can be 20,000, can be 6 billion. I don't care. Okay, as long as it is one concrete value, one concrete real number, it will meet this requirement. And if this requirement is met, then we say f of n is an element of big O of g of n. But what does that mean, Tack? Well, all it means is g of n is an upper bound of f of n. That's all it says. Now, how good is it an upper bound? It doesn't qualify. In other words, if g of n is not a tight bound and instead g of n is a gross overestimate of f of n, this number here, the lim sup of this absolute value, can be 0 because f of n is growing so much slower compared to g of n that the minimum of all the maximums would turn out to be 0, okay, as n approaches infinity. And that's perfectly fine because I'm just going to ask you the question, is 0 less than infinity? The answer is, yeah, it is less than infinity. So that will still make f of n an element of big O of g of n. Now, this is all kind of abstract, right? So let's put concrete examples into this. Let's just say that f of n is just n itself. It's linear. And then g of n is n squared, okay? So now you have n divided by n squared, right? And n divided by n squared is 1 divided by n. So when n approaches infinity, even from your pre-calc class, when you understand the concept of limit, you go like, oh, okay, that approaches 0, okay, because 1 divided by n, as n becomes, approaches infinity, then 1 divided by n is going to approach 0, which means lim sup of this entire thing is just going to be 0. So the question now is that really true, Tack? If a particular algorithm has a linear time complexity, it will still be an element, it will still be in big O of n squared. The answer is yes, okay, because big O, all it says is it is an upper bound, okay? We can be grossly overestimating or we can just be barely overestimating. But that's all it says, okay? It's just an upper bound, sorry. We're going to ignore negligible because it's very seldom that it becomes actually useful. So we're going to ignore negligible. And instead, we're going to skip to lower bound. So when you look at lower bound, you will say, oh, this looks a whole lot like upper bound. Instead of big O, we have big omega here. Instead of lim sup, we have lim inf, okay, limit inferior. And instead of being less than infinity, we just have greater than 0. Yep, that's it. That's how we say g of n is a lower bound of f of n. Alright? Because if you think about it, okay, how can we make sure that f of n divided by g of n when we take the absolute value of this? Now, the absolute value is not particularly helpful, even though it doesn't hurt anything. It's not particularly helpful because f of n is a time complexity function. It is the exact time complexity function. And then g of n is just a simple function that we are using and go like, can we just, instead of looking at this really long formula, can we just say that it is about this, and call it a day? That's the whole idea of g of n, right? So they both have to be non-negative because we cannot complete an algorithm in a negative amount of time. So the absolute value is not really needed, but it doesn't really hurt anything either. So now getting back to our example here. So f of n divided by g of n, as long as it is greater than 0, in other words, as long as g of n doesn't grow way faster compared to f of n when n approaches infinity, then we're going to call g of n a lower bound of f of n. Then some of you are going to say, what if f of n is n squared? Okay, what if this is n squared, and what if g of n is the log of n? Okay, that is, as you probably know, n divided by the log of n is going to approach infinity when n approaches infinity. So that means this answer here, this portion here, is going to be infinity. So would that still be, would it still meet this requirement? Well, then I'm going to ask you this question: is infinity greater than 0? The answer is yes, right? So because infinity is greater than 0, so that means, in that case, when f of n is really n and g of n is log of n, it is still a lower bound. G of n, which is log of n, is a lower bound of f of n, which is just n itself. I'm just using that as a concrete example here. Oh, okay, I see a phase in the text channel. I mean, the other way you can look at this is f of n is just n, and then g of n is 1. Then f of n divided by g of n is just n itself. When n itself approaches infinity, the whole expression here, the limit inferior function, is also going to approach infinity. And so the question is infinity greater than 0? The answer is yep, it is. And as a result, in that specific example, f of n, which is n, is an element of big omega of g of n, which is just 1, okay, the constant of 1, which basically means constant time, is an underestimate of linear. It doesn't tell you a whole lot. It's not very useful, but it is still a lower bound. And then the next concept is dominant. And we can skip this one too because it's really not particularly useful. So we're going to skip 3.9 and then we go straight to 3.10. So 3.10 is big theta. Okay, this notation here is big theta. So big theta is actually what we really want. Okay, if you ask any computer scientist and go like, okay, I'm giving you this algorithm. Is it useful to derive big O? Is it useful to derive big omega? Or is it more helpful to derive big theta? The answer is, well, you kind of need the other two to get to big theta, but big theta is what we really want, okay? Because big theta means g of n is a tight bound of f of n. Now, how is that defined? Well, I think we have seen this before, right? F of n is an element of big O of g of n. That's the first thing that we talked about after we discussed exam 2. And then the other one is f of n is an element of big omega of g of n. Same g of n in these cases. So we want g of n to be both the upper bound and also the lower bound. I think one of the cats has a plastic bag attached to it and is running around the house. Yeah. I have no idea what is going on, but I will find out after the end of the class. Alright, so if no, they were fed already. They're not hungry. So if g of n is both the lower bound and the upper bound of f of n, then we call it, big theta. So we really want to find out, big theta in most cases because we want a tight bound on the time complexity of an algorithm. So that's kind of the bottom line. All right. So, do we have any questions about these concepts? So at the very end of the entire module here, okay, big theta is what we want. But in order to define big theta, we need to define big O and a big omega. So when you look at big omega, we need to understand what is limit inferior. And then when you look at upper bound, we need to understand what is limit superior. So limit inferior by itself is the supremum of a bunch of infimums. Now, remember what I said, because we are dealing with real numbers. In other words, the x of k's are always real numbers. So because they're real numbers, they are totally ordered. If they're totally ordered, they're also automatically partially ordered. But being totally ordered means, instead of using infinum and also supremum, we can basically say, oh, okay, you're really just talking about maximum and minimum. Okay, so maximum is the same as supremum, and then minimum is the same as infimum when we are dealing with real numbers. So limit inferior is really just, the maximum of the minimums. Now, what minimums are we talking about? These minimums, they just have a different starting point of the sequence of x. Okay, so each minimum is the minimum starting at a different place of the entire series. That's all. And then we have limit superior, which is kind of the same as limit inferior, except we flip, which one is inside and which one is outside. So this time we are finding the minimum of the maximums. Okay, so one is placing a cap on everything. The other one is putting a bottom to the whole thing. And the reason why we need limit superior and also limit inferior is because some functions are oscillating. They do not die down to a single value. There's no actual limit. So if there's no actual limit, then the whole concept of just just using limit is not going to work. So that is the reason why we have supremum and why we have limit superior and limit inferior. So in order to define those two, we need to understand what is infimum, which is basically just the minimum of something. But this is how we state the minimum of something using a universally quantified statement. And then supremum is kind of the same thing. If we want to use a universally quantified statement, this is how we basically say, yep, of all the values, this is going to be the one that is the least of everything that is more than at least as much as the values of the values in x. Okay, that's it. So and then from this point, we kind of go back and talk about asymptotic estimates, which you have some exposure to, since you have taken at least pre-calc. The whole concept of asymptotic, should be a part of that class. Maybe. I haven't taken that class, but I think, pre-calc needs to talk about asymptotic behavior, because we are we are looking at the slope between 2 points. Okay, that's the concept of calculus in differentiation. So you're trying to make the distance between the 2 points, horizontally as close as possible, and then measure the slope, the same way. And you want to make the delta x, approach 0, and that's kind of looking at asymptotic behavior. All right, and that pretty much explains, backwards. Okay, explains this entire module. Do we have any questions about this module, regarding the terms? All right, so we have about 6 minutes remaining. So we are slightly ahead of time compared to how I usually teach this class. So we are currently at this point. So we can continue to talk about recursive definition and algorithms, and also different categories of time complexity of recursive algorithms. Okay, so that's one way to proceed. The next way to proceed is to skip these two sections and then go straight to graphs. Now, graphs is one thing that we have to talk about because it is a very kind of distinct kind of topic, and I think it is quite important to go over graphs. Same thing for predicate calculus. Now, predicate calculus has a relation, is related to propositional calculus. Okay, so those two are kind of related. One is different only because it has quantification. So predicate calculus is kind of like propositional calculus, but it has quantification. Now, because of the quantification, it kind of changes a few things. And also, the fun thing about practical calculus, we can actually, do things with it. With propositional calculus, you guys just have to go through a whole bunch of Boolean algebra manipulation, get to the CNFs, and then do a bunch of resolutions. Well, that's kind of, I guess it's fun for some people. If you like to prove theorems and stuff like that, it's kind of fun. But practical calculus actually is more fun to people who like to write programs, okay? Because there's a programming language called Prolog, and all it does is to say, okay, give me a bunch of predicates, and I'll tell you what is true and what is not. Okay, so this is definitely one of the topics that we want to go over because it's really kind of important, for this class. So there we have it. I think what I'll do is I am going to continue with graphs, skipping recursive definitions and algorithms and also categories of time complexity. So I'm going to skip these two links and go straight to graphs. And then after that, we'll go straight to predicate calculus. Now, if we do have time, at that point of this class, then we'll probably go back to talk about recursive definitions and algorithms. CISP440 is a co-requisite of this class, so I'm pretty sure at this point everybody has exposure to recursive definitions. So as it turns out, recursive definitions are very, very useful when you want to show an algorithm is correct because it lends itself to a specific proof technique. Can someone remind me what kind of proof technique lends itself to recursive definitions? Yep, proof by induction. Very good. Okay, so that relationship is very important, okay, because as much as I would like to consider this class to be, oh yeah, this class is kind of fun, we are talking about a lot of important topics, this is still considered a lower division class at a 4-year university. In other words, what we are teaching here is really just to prepare you to get started with some of the upper division classes that you'll be taking once you transfer to a 4-year university. So from that perspective, understanding the importance of recursive definitions is really, really important. I think a lot of people do not understand recursive definitions, or they have some anxiety when people talk about recursive definitions. I think the main reason is because they're overthinking. Yeah, really. I mean, we're talking about something that is actually intrinsically fairly simple, but people look at it from a certain perspective and it makes it harder than it needs to be. So if I have time left at the end of this semester, I would definitely want to go back to talk about recursive definitions. It's more about a way of looking at things rather than a technically difficult kind of thing. So it's kind of like procedural versus object-oriented. It's a way of looking at things. You can get things done either way. It's just a way of, okay, how do I want to look at it? So recursive definitions is one way of looking at things. And once you get a hang of it, of how to convert a very common, usual, non-recursive algorithm and say, oh, okay, so to turn it into something that's recursive, it's just this simple. Once you get that concept, once you understand why it is easy, I think it's going to be very beneficial to many of the other classes that you're going to have to take after you transfer. So I would definitely want to get back to this one if I can. So I got 40 seconds remaining. So for Wednesday, I want you guys to kind of do the question that I had earlier. I can post it in the text channel. I'm going to post that file in the text channel. But on top of that, I want you guys to pre-read the graphs module. Because the graph module is kind of getting back to programming a little bit, okay? Because I think most of you are kind of missing, oh, I wish this class talks about algorithms. I wish this class actually has algorithms that actually do something instead of giving us all the math stuff, that doesn't seem to go anywhere. So this module does have two algorithms, not one, but two. One is called the A-star algorithm. One is called Dijkstra's algorithm. They try to accomplish kind of the same thing, but they are also different in certain ways. So read ahead of me, into the graphs module before Wednesday, and then we'll talk about, the two algorithms, and generally just kind of talk about what problem we are trying to solve with those two algorithms. So that's kind of the plan for Wednesday. Any questions? All right. So we are. Yeah, there are a few things to review. General graphs. Well, we are only concerned about digraphs or directed graphs, where edges are unidirectional. You can only go in one direction. So if you want to get a really, really quick, kind of idea of what we'll be talking about, it's kind of like, okay, so you're working for Google and you're part of the Google Maps, project. You can measure the time, how much fuel is needed to go from one point to another point, and then now you have customers who are asking, so how do I go from here through all of these various points to over there? Give me the route that will save me the most, save me gas. Give me a route that will save me time. Okay, so depending on whether you're optimizing for fuel or time, okay, you want to be able to generate that route. Okay, so you have a starting point, you have an ending point, but you want to find out how to go from the starting point to the ending point in either the shortest, in terms of time, or shortest in terms of fuel path. So both algorithms will accomplish that. One is kind of blind. One is just saying, okay, I'm just going to keep expanding and expanding and expanding until I touch the destination and I'm done. The other one is quote unquote smarter. It makes use of rules of thumb, otherwise known as heuristics. So that's the difference between Dijkstra's algorithm and the A-star algorithm. So that's going to be something that we'll talk about on Wednesday. I think we'll get through terms for sure. I'm pretty sure we can get to start with Dijkstra's algorithm, and we might be able to go through one sample run of Dijkstra's algorithm on Wednesday. So I would definitely get through section 4 before class on Wednesday. All right. All right. Yep. You guys are welcome. Thank you for being here, and I'll see you guys on Wednesday.